Hi there guys, so welcome back to my next video. This one will be continuing on the concept of electronegativity, but we'll be looking at it in organic chemistry, and particularly looking at it in mechanisms and basically helping us determine why mechanisms work as they do. So let's just kind of recap. So obviously if we've got, let's say, a carbon atom bonded to a fluorine atom, the fluorine atom is more electronegative than carbon, so therefore it attracts electron density, the electrons in the covalent bonds, to a greater extent than carbon does. Therefore the electrons will be positioned approximately there in the bond. Or another way we can draw that is we can actually draw that with some arrows. So we can basically just say that the electron density is going towards the fluorine. So that is another way of drawing it, which I will be using this way in this video. So let's take a look at the most simple alkene. So we've got ethene or ethylene. So 4 hydrogens, 2 carbons, and a double bond in the middle. Okay, so let's look at the halogenation of ethene. Okay, so if we add hydrogen bromide, we obviously form, I'm going to write this shorthand, CH3, CH, and then Br. Okay, so let's just quickly look at the mechanism for that. So if we draw out our hydrogen bromide molecule, okay, obviously bromine is more electronegative than hydrogen, so we can draw the arrow like that, which shows electrons are more attracted to bromine. Okay, now because this double bond, it obviously consists of a pi bond where the p orbitals overlap sideways, okay, like that, as well as a sigma bonds where the orbitals overlap head on. Okay, so this basically means that electron density is greater. Okay, so this will actually attract our hydrogen atom because it's electropositive, whereas the bromine's electronegative because of obviously the sorry, it's slightly positive. So hydrogen is slightly positive, bromine slightly negative. Sorry. Okay, so what happens is we have these the electrons in the pi bond. Okay, they basically are attracted to this hydrogen molecule. Right, we can draw that with a curly arrow. And then this then proceeds, obviously because hydrogen can only form one bond at a time because it's only got that one outer electron. The electrons in the hydrogen bromide bond, they actually go towards the bromine. Okay, so that then basically leaves us with an intermediate compound. So I'll draw this out full. So we've got our CH3 where the hydrogen forms a bond, so it basically goes like that. And then on the other carbon, because this carbon now has basically lost this bond, so this bond's broken, it's left with only 1, 2, 3 bonds. Okay, so this actually becomes a positive ion because it's got 1 less electron. However, because this bond down here, this one broke, okay, and both electrons went to the bromine, which means that the bromine is now, well, the bromine atom is now a bromide ion. So we have a negative charge and a lone pair of electrons. Okay, or an additional lone pair of electrons, let's say, because obviously it's still got 3 around the side, 3 others around the side anyway. Okay, so now what happens is because we've got positive, and negative, obviously we have movement of electrons again, and that forms our final product, which is that. Okay, so let's have a look at this in a slightly different sense, to help us basically determine, because this is obviously it's a very simple molecule. Okay, ethene. So there's only one possible outcome of the final compound. Let's have a look at an example with, let's do, okay, so let's have CH3 here. Okay, let's have carbon, let's have a methyl branch up here, double bond to another carbon, obviously a hydrogen here, and then the CH3 on the end. Okay, so this is obviously an asymmetric molecule, which will basically change what the molecule actually, what the final haloalkane will look like. Okay, so let's just use chlorine to make it a bit less boring than it already is. So let's do chlorine. Okay, so obviously we have our slightly positive, slightly negative, and we can even draw a little arrow to show that electron density is towards the chlorine. Okay, so let's do our curly arrows again, like that, and then we can do another one like that. Okay, so exact same thing as before over here, exact same thing, but just with the hydrogen and chlorine. Okay, so what happens now is obviously we could actually form two different compounds. The hydrogen could either bond to this carbon atom, or it could bond to this carbon atom. Okay, so let's just draw out both of them, and then we can determine which one we think is more appropriate. Okay, so let's do it. Let's say it bonds to this carbon atom to start with. So we've got hydrogen, that will be electropositive, and CH3. Then we have our bromide ion. Okay, not bromide, chloride ion, and our chloride ion with our lone pairs. Okay, or we could obviously have our CH3, carbon, CH3, CH with our hydrogen here. Okay, CH3 and our carbon cation in this position, as opposed to that one. And again our chloride ion. Okay, so which one is actually more likely to form? Because obviously in solution there's millions and billions and even more than that of molecules when they actually react. Okay, but we have to actually, so obviously you will get a combination of both of them, but it's more about which one is more likely to form. Okay, so if we just come over here, and then we can come back to that bit later. So if we just have this does lead a bit away from electronegativity, but it is still quite linked. So you actually don't have to know all the details in this for A level, but I think it is still quite useful. So let's say we just draw the most simple organic compounds ever, basically. So we have a methyl ion. Okay, and if we contrast that to, let's say, a tertiary carbon cation, okay, like this. So this is called the inductive effect. Okay, and what it basically is we've got this obviously strong positive center in both of them, which will want to attract the electron density from all the neighboring groups. Okay, so if we draw our arrows again, even though carbon is more electronegative than hydrogen, okay, because it's more electronegative, then it will obviously attract a bit of electron density, but more so because it's a positive ion, which means it attracts to a much greater extent. However, in these little hydrogen groups, we only actually have one electron in total, just in this outer shell. In these groups, we obviously have 9 electrons, so we have 6 from the carbon and 3 from the hydrogen. Okay, so we have 9 electrons total from each of these groups. Obviously, 9 is far greater than 1. So the electrons, they are much greater attracted to the carbon. Okay, because they're bigger groups, they can donate more electron density, so they're far more attractive to the carbon cation center. Okay, so why this is important is because this will basically increase stability. Okay, so it increases stability because they're more attractive, so the compound's more stable compared to this one, compared to number 1. Okay, so 2 is more stable than 1. Okay, in terms of stability. If we then relate this to these compounds here, okay, we can see that number 1 is much more resembled by this one, because it has one hydrogen and then obviously one carbon with another methyl group. In this one, okay, we have methyl group, and obviously a pretty strong methyl group in this situation here as well. Okay, so we've got all this electron density flowing towards the carbocation, okay, which makes it far more stable, which therefore means that this one is the major product and this one is the minor product. Okay, you can also look at this by whether the carbocation intermediate is either primary, secondary, or tertiary. Okay, so this one is tertiary, this one is primary. Sorry, this one's actually, yeah, tertiary, primary, which therefore means that it's much more stable. Okay, so that's that. Okay, we're also going to look at, I want to look at this in another sense. Okay, so let's say we had a very similar compound. Okay, so we had a carbocation, but instead of having methyl branches, we had phenyl branches. Okay, so I'm going to draw the benzene. I'm going to draw a Kekulé structure because we can show basically the stability better. Okay. So let's say it looks something like this. Okay. What actually happens is we basically get resonance. Okay. So we get loads of intermediate forms where it increases the stability much greater. So what we get is we basically get a curly arrow that goes from here to here, and then we get this one goes from here to here, and then this one goes from here to here. Okay, as one of the options. So if we start off by drawing out the one from the first one, we have, I'm just going to write phenyl on this bit to shorten it. So we have a double bond here, okay, and this carbon here, this is now left without a bond, so this is electropositive, and then that's a double bond, okay. What we can then have is we can then have this double bonds basically forms, gets exchanged with the carbocation in there because it's electron dense. So we then get our phenyl branch again, phenyl branch with our other form. So we have that's still a double bond, and then that one, and then we have our carbocation in there. Okay, and then we can have one more variation where that goes like that, and then we're left with this one that's positive. Okay, so we have 1, 2, 3 different variations just on this one. That would be the same for this. So we'd have 1, 2, 3, 1, 2, 3, and then another one here. Okay, from the original. So that basically means that we've got 10 different arrangements compared to only one arrangement with this one, because you don't get any double bonds forming in these intermediates, just because there's not enough atoms and there's not enough other double bonds to do it. So this conjugation, we call it, increases stability even greater than what we would have here, which is why these intermediates are much more stable than this one and significantly more stable than that one there. So I hope you guys enjoyed that video. I'll upload another one soon, not sure what it will be on. Maybe some more organic concepts, and really understanding how mechanisms work and reactions, curly arrows, all stuff like that. So yeah, thank you for watching, and I'll see you in the next one.